We talked about Newton. We talked about Maxwell. That takes us in the 20th century in terms of unification. There's a guy named Einstein on
Mhm.
whom you wrote a book who did
Right.
quite a lot of progress on the effort of unification.
Sure. So Einstein, he's a pretty amazing guy. In 1905, he had his miracle year where he wrote multiple papers. The one that most people know about is special relativity, where he showed something that makes no sense to anybody who's not really dug into it very hard. And that is that two people experience time differently. Time, is a fascinating thing. We don't really understand what time is, which is weird. You think that that'd be something we'd understand very well, but we really don't. We know a lot about it, but really understanding it, not so much. But Newton thought that time was just universal for everyone. So my time, your time, some person's time on Mars or on Alpha Centauri, everybody experienced time the same. What Einstein showed was that that wasn't the case, that different people moving at different speeds with respect to one another experience time differently, which is absolutely a mind-blowing concept. Now, most people think that Einstein then said, well, he invented space-time, that space and time are the same thing. And he was behind that, but that actual insight came from one of his teachers, a guy by the name of Minkowski, who looked at Einstein's equations. Minkowski was a little bit more mathematically inclined than Einstein. And he saw that if you look at the equations, you have basically one person's space and time equals some numbers times this person's space and time. And so that's kind of a staggering thing. So that is where Einstein and Minkowski really did this unbelievable concept that space and time are actually pretty much the same thing. That runs afoul of our understanding of how the world works because time just moves, it's continuous. We know what it is at a visceral level, in an experiential level. We might not understand it on a formal level, but we know what time is. It's what makes today today and not yesterday or tomorrow. Space is a little different. You can walk somewhere, you can walk back, you can move around. You have more freedom to move in space than you have to move in time. You can always move forward in time. It's just moving backwards that turns out to be a little more difficult. But yeah, Einstein's understanding that that is the case, it caused everybody to think about the world very, very differently. And that was in 1908 when Minkowski really laid it out in a strict space-time.
And that also led to the work on special relativity, led to the speed limit, the speed of light.
Well, it was a premise. He had two premises. One was that the laws of nature are the same for everybody. So if you're moving at some speed, or if I'm moving at some speed, I can say I'm not moving and saying you're moving at some speed. That's not controversial. That is what we call Galilean relativity. It's from hundreds of years ago. But what Einstein said that was controversial was that everybody measures that the speed of light is the same, irrespective of how we're moving with respect to each other. You'll measure the speed of light to be a number. I'll measure the speed of light to a number. And that's very, very different from what Newton would have said or Galileo or any of the old guys. And it was taking those two things together that caused all of the weirdnesses of special relativity. Now, you could then very easily say, well, that second premise that everybody measures the speed of light to the same is just dumb. And you could test that. So that's where testing relativity comes in. And Einstein's equations, which include those two assumptions, it predicts the behavior of everything perfectly well. Now, we've actually measured, done experiments where we can say that the speed of light is the same for everybody. That's not how that's been in the beginning. It was really that assumption leads to predictions. The predictions are true, so the assumption is true. Now, there is for those people, for your viewers who want to say, well, how do you measure that the speed of light is the same for everyone? The particle physicists do this. And the way you do this is the following. There are some subatomic particles that, when they decay, they emit light. That's their decay product. And so you collide two things together so you know when the particle was created. Then you have surround your collision point by a detector, and you measure how long it takes for light to get to your detector. And by God, it's the speed of light, which it should be. However, sometimes in these collisions, some of these subatomic particles you make are coming out at very high speed. They might be coming out at 95 or 97 or a very large fraction of the speed of light. And then they decay into photons. And so you measure how long it takes for the photon to get to your detector, and it says light travels at the speed of light. Now, if it were that if Einstein's conjecture was incorrect, you'd have a particle coming out at near the speed of light. It would be decaying into a particle traveling at the speed of light. Then that particle should have traveled at, say, 2 times the speed of light or something like that. So it should have taken half as much time to get to the detector, but it doesn't. So this is a hard, serious measurement that shows that something, we can measure the speed at which light comes out of this stationary created particle, and it's the speed of light. Then we can measure what the speed is of it coming out of something that's moving, and it's still the speed of light. So that is an actual measurement, but that is not something that was possible in Einstein's day, but it is now.
Just to take a small tangent, how weird is it in the full ranking of weirdness that is physics? How weird is it that there's that speed limit of this speed of light?
Well, I have to tell you, when I first encountered this, it's pretty freaking weird. It's like pegs the weird meter. But as you become more familiar with it, as you become more comfortable with the idea, the thing to remember is the speed of light. It's the speed of light through space-time. Once you embrace that, that makes a whole ton of sense. It all of a sudden makes everything fall much more into place. I think that there is an ultimate speed isn't that shocking. It just simply says that it's a property of space in the same way that there is, space can transmit a certain strength electric field. It can support a certain things. Whatever space is, and we don't know what space is, but whatever it is, it has the capability of transmitting these things at that one speed through space or time. And everything else comes from our insisting that we keep space and time different. That's how I view it. And at least for me, that once I accepted that, it all became very comfortable.
So the nature of my question actually here that will apply over and over is trying to empathize, trying to put ourselves in the shoes of the people before space and time were unified
Yes.
into space-time, and really experience and think through how difficult of a leap is that.
Huge.
The reason I sort of say that is we are now in the modern day in the 21st century. And of course, we're going to have to make leaps like that in our future. So what are the unifications we're not seeing in front of our eyes? So for example, there's so many examples through your work, through your lectures of Paul Dirac taking antimatter seriously, looking at what the math shows and saying, I really think this thing exists.
Right.
I mean, it just sounds insane.
It does.
And so I think this is a good warm-up. The space-time unification is a good warm-up as we march through the 20th century, because it gets, in my view at least, weirder and weirder, even with Einstein himself.
Well, let me give you an even more basic example. Sodium and chloride. Sodium is an explosive metal. You put it in water, and it's kind of neat. You put it in water, and it doesn't quite explode, but it gets hot, and it pops around. Chlorine, it's a gas. It's going to kill you. So these two things are deadly. They're awful. And yet when you mix them, you put it on your food at night. It's salt, right? And so this is a case where this whole A, unification, and B, this deeper understanding, in this case of chemistry, of how two things that are dangerous can be brought together and turned into something not only innocuous, but necessary for human life. And so this is not unusual, that what you're describing. I mean, when you think about it, forget about everything else. Just the fact that, we tell little kids that the world was made of atoms. Now, that's crazy. Most people have never seen atoms, and yet nobody really doubts it anymore. And I think it's just a case of familiarity, and then the culture slowly accepts it, and it's real, even without the evidence. In fact, one of the courses you described there, how we know what we know, I think that's a valid question. How do we know there are atoms? And of course, there are ways we do.
And by the way, on that front, I would love to go through how we know the building blocks in the universe as we march towards quarks. That, in the course that you mentioned, is one of the most fascinating things of this philosophy of atoms being around for a very long time. Then you concretize and you actually can prove or have strong observations that indicate that there is atoms, and then there is a nucleus, there is electrons, there is photons, there is quarks and leptons. I mean, it gets weirder and weirder, and now we're facing the mystery: is there building blocks even smaller than that?
Mhm.
But anyway, Einstein, turns out, didn't just do special relativity. By the way, I really think he deserves 3 Nobel Prizes. He got it for photoelectric effect. The fact that he didn't get it for general relativity is a crime against humanity. I don't understand. Obviously, he should have gotten it for general relativity and special relativity. I
Mhm.
mean, I think special relativity is separate for general relativity in terms as far as Nobel Prizes go. So general relativity is another unification.
Yes, that's right. What Einstein realized was that if you were in a rocket ship and the rocket ship was a very quiet rocket ship and it was accelerating, it would feel like you were experiencing gravity. And so, as you say, it's one of his happiest moments when he realized that acceleration and gravity feel very much the same. What I'm impressed by is that idea, which is already a pretty neat idea, somehow led him to take his space time idea, take this acceleration gravity idea, and realize that he could describe gravity as the bending of space-time. Space-time being constant, like east, west, north, south, that's already hard enough. But now he's saying, well, take your map and crinkle it and bend it and so forth, and that's gravity. That is a staggering, mind-blowing idea.
I guess I wonder if you can comment on what do you think is the idea generation process that leads to that. So it probably, in Einstein case, has to start with what if gravity is itself space-time geometry? You have to have a thought like that, right?
Yes, I think so. There's a lot about science. There's, of course, knowing what went before. There is knowing the mathematics that allows you to figure out the implications of your theory. There is the discipline to argue with yourself and other people because most ideas are wrong. But then there's what you just described, that intuitive spark. And that is something that is very, very difficult to create. There's a reason that we venerate these people is because it is an unusual feature, and most people only have that aha moment once in their lifetime, if they have it at all.
Hmm.
And then there's a tricky business because I'm sure you do, and I get a lot of letters from creative thinkers who don't have all of the history and the mathematical discipline and the self critique that's necessary. And so they come up with these ideas, and often it's easy to see where they just don't play out. Um, so in order to be that person who changes the way we see the world, ideas themselves are not enough. These creative ideas, that's not enough. You need it with the discipline and the critique. And it's that amalgam of those things that make you a genius that history remembers.
But it's hard to know in a field of people you might be tempted to call crazy. There could be geniuses there, and it's hard to know which is which. We should mention that Einstein himself couldn't see the genius in quantum mechanics initially. Couldn't see the correctness, I should say. So he could see the insanity of gravity bending space-time, but quantum mechanics was too weird for Einstein.
In all fairness, it's weird for me too. But the thing is, even while that is true, and Einstein maybe spent the last few years of his life trying to to blend electricity and magnetism and gravity in a single thing, and he was unsuccessful. But he still was a very, very valuable critic of quantum mechanics. It's not that he didn't understand it, because he did understand it. He thought about the implications and all this quantum entanglement business, not all of it, but he was responsible for saying, well, if you're right, then this. And of course, then people went out and found out that Einstein's implication of quantum mechanics was real. And so they could say, see, quantum mechanics is real. So he was thinking deeply about it, and he was doing exactly that thing I said. There's that spark idea, but there's that critique idea.
Mhm.
And if you're able to critique an idea, you might kill it. And it's always depressing when I have this brilliant idea and it gets killed, but it's better to be killed than to keep it around and waste time on it. And so he was, in that case, not generating the aha, but he was saying is, all right, let's take your aha. Let's see it's right. What does it mean? It means this. That allows people to go test it. And so he was contributing very crucially to that other part of scientific advancement, which is not just the aha moment, but the beat it to death, test it, critique it, and make sure it's real. And it's only after all of that has been done that you really are sure you're right. And that's why science is such a powerful tool. It is that combative, just downright kind of jerky critique that most people don't like. They don't like people saying, your ideas, might be wrong. But it is crucial. It's a crucial part of the scientific process.
Plus, there's that quote on the other side of it that I've heard you mention, which is, I believe your idea is crazy, but is it crazy enough? Was that
I
Niels
love that one.
Bohr?
Yes. We all agree that your idea is crazy, but is it crazy enough?
And there is some degree of taking those leaps of crazy, but it has to be backed with rigor.
Right.